Imagine a ship carrying thousands of shipping containers stacked higher than a 10-story building, a vessel weighing hundreds of thousands of tons, moving across an ocean where enormous waves can push it from side to side. Now imagine all of that cargo sitting above the waterline. It sounds like the perfect recipe for disaster. So why doesn't the ship simply tip over? How can a container ship carry more than 20,000 containers without becoming too top-heavy? And what happens when a ship like this enters a violent storm? The answer isn't one single piece of technology. It is a combination of physics, hull design, weight distribution, ballast systems, container locking systems, and careful loading. And the most important part of the answer actually begins underneath the water. A container ship may look enormous from the outside, but most of its real engineering is hidden below the surface. The hull is shaped to push water aside, and that displaced water creates an upward force known as buoyancy. The ship's weight pushes downward, while buoyancy pushes upward. When those forces are balanced, the ship floats. But floating is only the beginning. A ship can float and still be dangerously unstable. Imagine placing a small wooden block in water. It floats easily. Now imagine placing a tall tower of heavy objects on top of that block. The block may still float, but it becomes much easier to tip over. The same basic problem exists with container ships. The containers can be stacked many levels above the deck, so engineers have to make sure the ship's center of gravity remains in a safe position. This is where the underwater hull becomes extremely important. A container ship is not shaped like a simple flat box. Its underwater hull is carefully designed to provide stability. The width of the hull, the shape of the sides, the depth of the ship, and the distribution of its mass all affect how the vessel responds when waves push against it. When a ship tilts to one side, its underwater shape changes. More water is displaced on one side than the other. That changes the buoyant force, and the resulting force creates a restoring tendency, pushing the ship back toward an upright position. This is one of the fundamental reasons large ships can survive waves. But engineers don't simply rely on the shape of the hull. They also control where the weight is placed. This is one of the most important secrets of container ships. Not every container weighs the same. Some containers may carry relatively light cargo. Others can be extremely heavy. If the heaviest containers were simply stacked at the very top, the ship's center of gravity would rise. That would make the vessel less stable. So loading a container ship is much more complicated than simply filling every available space. Computer systems are used to plan where containers should go: weight, destination, container type, stability, all have to be considered. A heavy container might be placed deep inside the ship, while lighter containers can be placed higher. The goal is to create a safe distribution of mass. And there's another challenge. Containers are not all going to the same destination. A ship may visit several ports during one journey. That means the loading plan has to consider what cargo will be removed first and what cargo will remain on board. Imagine a ship carrying containers for 5 different ports. The containers for the first port are buried underneath containers for the final port. The crew would have a serious problem. So the loading sequence has to be planned carefully. The ship needs to remain stable while also keeping the cargo accessible. This is why modern container terminals use sophisticated software to plan loading operations. But even with perfect planning, the ship still needs another system: ballast. Inside large ships are massive ballast tanks. These tanks can contain seawater. By taking water into different tanks, the ship's weight distribution can be adjusted. If the ship becomes uneven, ballast can help correct the imbalance. If the vessel is riding too high, more ballast water can be taken on board. If it needs to become lighter, water can be pumped out. This gives the ship another way to control its position in the water. And ballast isn't only about stability, it can also help maintain the ship's draft. Draft is the distance between the waterline and the bottom of the hull. A ship carrying a huge amount of cargo sits deeper in the water. A ship with less cargo sits higher. Engineers need to make sure the vessel remains within safe operating limits, because the ocean isn't always calm. A ship that is perfectly stable in calm water can experience enormous forces in a storm. Imagine a massive wave approaching from the side. The wave lifts one side of the ship, while the other side drops. The ship begins to roll. For a small boat, this movement can be dramatic. For a container ship, the consequences can be much more serious. Thousands of containers are stacked above the deck, so the cargo itself becomes part of the stability problem. But this is where another remarkable engineering system becomes important. The containers are not simply sitting on the deck. They are mechanically connected to the ship, large steel fittings called twist locks, and other securing systems connect containers together and to the ship's structure. These systems help prevent containers from sliding or separating during violent movement. Think about a giant stack of boxes. If you simply place them one on top of another, a strong sideways force could knock them over. But if the boxes are connected together, the entire stack behaves more like one structure. Container ships use this principle on a gigantic scale. The containers form organized stacks, and the securing equipment helps keep them in position. But even the strongest securing system has limits. That is why loading remains critical. If containers are too heavy, too high, or badly distributed, the ship can experience dangerous stresses. And this leads to another hidden problem: the ship itself can bend. A container ship can be hundreds of meters long. Imagine a structure that long moving through waves. The middle of the ship might be supported differently by the water than the ends. Sometimes the bow and stern are lifted by waves while the middle is lower. Other times the middle is lifted while the ends are lower. These movements create enormous forces along the hull. Engineers call these conditions bending and structural stresses. The hull has to be strong enough to handle them. Inside the ship are massive structural components: steel beams, frames, longitudinal reinforcements, and strong bulkheads. They work together to distribute forces throughout the vessel. The ship is essentially a gigantic steel structure designed to flex within controlled limits. But there is another surprising feature of modern container ships. The ship doesn't necessarily need to remain perfectly upright every second. A little rolling is normal. The important thing is that the ship has enough stability to return toward its upright position. This is why a container ship can look terrifyingly tilted in a large wave, yet still recover. The ship rolls, the underwater hull changes position, buoyancy changes, and the restoring forces act against the tilt. But what if the ship encounters a truly extreme storm? This is where forecasting and route planning become part of the engineering system. Modern container ships don't simply leave port and hope the weather stays calm. Operators monitor weather forecasts, ocean conditions, wave heights, wind speeds, and storm systems. If dangerous conditions are expected, the ship may change its route. Sometimes a longer route is safer than heading directly through a storm, because avoiding extreme waves can protect both the vessel and its cargo. And cargo itself can create another danger. Imagine thousands of containers moving together. If one container breaks loose, it can strike another that can cause additional containers to become unstable. In severe cases, containers can be lost overboard. This is why cargo securing is taken extremely seriously. But the ship also has systems for dealing with water. A container ship is designed with watertight compartments and doors. If water enters one part of the vessel, the goal is to prevent that water from spreading throughout the ship. The hull is divided into sections, so a localized problem does not automatically become a total loss of buoyancy. Again, the strategy is not to defeat the ocean with one giant wall. It is to create multiple layers of protection: hull shape, weight distribution, ballast, cargo securing, watertight compartments, weather routing, and constant monitoring all work together. And there is another reason these ships can carry such enormous loads. They are designed around the physics of displacement. The heavier the ship becomes, the deeper it sits in the water. As it sinks deeper, its hull displaces more water. More displaced water means more buoyant force, so a ship can actually become heavier and continue floating as long as its hull remains capable of safely displacing enough water. This is why a huge steel ship doesn't automatically sink simply because it is heavy. The question isn't, is the ship made of steel? The real question is Much water does its hull displace compared with its total weight? A solid block of steel has a high density, it sinks, but a giant steel ship contains enormous volumes of air and empty space that increases the overall volume of the vessel without adding the same amount of mass. The ship's average density becomes low enough for it to float. This principle is simple, but applying it to a vessel hundreds of meters long, carrying thousands of containers, is an extraordinary engineering achievement. Now consider what happens when the ship unloads cargo. Thousands of tons may disappear from the vessel in only a few hours. The ship becomes lighter, and its draft changes. Ballast systems may need to be adjusted. Cargo distribution changes. The ship's center of gravity changes, and engineers have to make sure the vessel remains within safe stability limits. This is why a container terminal isn't simply a place where cranes move boxes. It is part of a carefully coordinated system. Huge cranes lift containers from the ship. Trucks move them through the terminal. Computer systems track their location, and loading plans determine exactly where each container belongs. A single ship can carry an enormous number of containers, but every container has a position, and every position matters, because on a vessel this large, small mistakes can become large problems. Now imagine looking at a container ship from the shore. You see a giant wall of colorful boxes, a massive hull, and perhaps dozens of cranes working around it. It looks almost impossible that such a structure could remain stable in open water. But underneath the surface, the ship is behaving like a carefully balanced machine. The hull is displacing water. The center of gravity is being controlled. Ballast tanks are adjusting the ship's weight distribution. The containers are locked together. The structural frame is handling enormous bending forces, and the crew and computers are constantly monitoring the situation. The ship doesn't stay safe because it is immune to waves. It stays safe because engineers designed it to respond to them. And that is the real secret. A container ship isn't simply a floating warehouse. It is a giant moving structure, a carefully balanced system of steel, water, weight, and forces. Every container has a place. Every tank has a purpose. Every structural beam carries a load, and every part of the ship contributes to stability. So when you see a massive container ship carrying thousands of boxes across the ocean, remember what is happening beneath the surface. Hundreds of thousands of tons are being supported by water. A huge steel hull is continuously displacing the ocean. The center of gravity is being carefully controlled, and the entire ship is constantly responding to wind, waves, and changing loads. It may look like a mountain of containers floating on the sea, but behind that image is one of the most impressive examples of applied physics and engineering in the modern world. And perhaps the most amazing part is that the ship doesn't need to fight the ocean. It simply has to be designed well enough to work with the physics of the ocean. That is how a vessel carrying thousands of containers can cross entire oceans, remain stable in enormous waves, and deliver cargo from one side of the planet to the other. If you enjoyed this documentary, subscribe for more fascinating stories about engineering, science, technology, ships, aircraft, and the incredible machines that make the impossible look completely normal. I'll see you in the next documentary.